Hello, everyone. My name is Yipeng Huang, and I'm an assistant professor at Rutgers University. Today, I'm delighted to share with you our paper at ASPLOS that's done in collaboration with my colleagues at UCLA and at Princeton. This is an excellent time to be doing research in quantum computing and quantum computer systems. The main reason is that for a long while, we've known about awe-inspiring algorithms. And at this moment, we finally have quantum prototype computers that are reliable and have enough capacity that we can at last finally run algorithms on the prototypes. And with this prospect, it's important now that we build out the hardware and software abstractions and stacks to enable widespread experimentation on prototype systems. So this talk today is going to be about using classical computers as a way to simulate and develop future quantum computer systems and algorithms, and about what kinds of intermediate representations and abstractions are helpful for us to reason about quantum programs. So in this talk, the key idea is that we will use techniques that we borrow from classical probabilistic inference as a way to reason about quantum computer programs. So this involves several stages of transformations. We're going to take quantum programs, which are phrased as quantum circuits. We're going to convert them into graphical models. And then we'll borrow techniques that were developed in classical inference to convert those graphical models into logical equations, into logical formulas that serve as useful intermediate representations that allow us to simulate and reason about the circuits. And this tool chain ends up being a useful basis for simulating an important class of algorithms that are useful, that may be useful in the near term. So at the bottom of the slide here, I have several pictures of several of the transformations where we take quantum circuits and turn them into graphical models, and then turn them into logical formulas, which allow us to do efficient inference and simulation of the circuits. So here's an outline of our talk today. We're going to go through several important pieces of the talk. First of all, I want to tell you about why variational algorithms are important in the near term. What are the special properties that make them useful on near-term quantum computers? Then I'll tell you about why quantum circuit simulation is important and what are the existing techniques that people have been using to do this kind of circuit simulation. And then finally, I'll tell you about our key insight, which is we can convert circuits into different intermediate representations that allows us to compile down the representations and then allow us to do efficient simulation of those circuits. All right. So first of all, we'll talk about our target workload, which is these class of variational algorithms that have a lot of attention because they may be the nearest demonstrations of useful quantum computing. So the key property of near-term quantum systems is that they have limited reliability, and also that they have limited capacity to run large quantum programs and quantum circuits. And with the existing capacity and reliability of those quantum systems, some of the important and famous algorithms, such as Grover's algorithm and Shor's algorithm, those algorithms are not going to be feasible to run on prototype systems in the nearest future. And so instead of those algorithms, which would solve problems like factoring and search, instead, near-term algorithms are going to involve some kind of interaction between classical computers and quantum computers using this class of algorithms that are called variational algorithms. All right, so now that we've motivated by variational algorithms are interesting and important, let's talk about the key properties of variational algorithms. So here's a template, a high-level overview of what variational algorithms look like. The key property is that these algorithms involve collaboration between a quantum computer on the left side here and a classical computer on the right side here. And the classical computer runs an optimization routine. This optimization routine is akin to using a classical computer running an optimization routine, which trains a set of parameters, very similar to training the parameters in a neural network. But here, instead of a real valued neural network, the parameters that we're training are instead inside a quantum circuit, which is executed on a quantum computer. And the quantum computer serves to evaluate a function, and the classical computer serves to try to minimize that objective function and come up with new parameters for the quantum circuit. And via this interaction between the quantum and classical systems, this is useful for solving their algorithms that use this scheme to solve interesting problems like optimization. And so using this collaboration between quantum and classical systems, the key result is that we're able to use existing prototype quantum computers, and we can use them to run meaningful computation without any error correction in the near term. And this is done by borrowing the strengths of both classical and quantum computation, where you use a quantum computer to prepare and measure a quantum state. And the classical computer helps by running a optimization routine and iterate the execution. And interestingly, these algorithms also have quantum circuits that are relatively wide but shallow. This means that the quantum circuits themselves have relatively few operations, but can do the algorithm on multiple qubits. And some of the prominent examples of these variational algorithms include the VQE algorithm. This has uses in simulating quantum mechanical systems, using a quantum computer to simulate quantum systems. And another class of such algorithms are what are called QAOA, quantum approximate optimization algorithms. And these can solve problems such as maxsat and maxcut. All right, so these types of algorithms, variational algorithms, are important and people want to study in the near term. And we want to try running them on quantum computers. And also, where possible, we can also try to use a classical computer as a means to simulate the execution of those algorithms. And so it's important to sometimes use a classical computer as a way to simulate the algorithm so that we build models of how the algorithms execute and to try to bootstrap the next generation of quantum prototype systems. And so simulating quantum circuits is important, and simulating variational circuits is doubly important. And so we'd like to talk about what are the unique properties that make simulating variational algorithms especially difficult and a distinct class of problems compared to other types of quantum circuits. And so here we have the properties of variational algorithms. So the variational algorithms have several interesting properties. So first of all, we talked about how these quantum circuits have relatively many qubits, but try to do relatively few quantum operations on each qubit. Secondly, because these algorithms involve an iteration between a classical and a quantum computer, this means that these algorithms will run many times, but with different parameters. And each time the simulation has to run, the overall circuit topology is the same, but the numerical parameters inside the algorithms may change. And so you want to have a simulator that's able to take advantage of this kind of property. And then thirdly, and finally, these algorithms work where the only information taken from the quantum circuit is a sample drawn from the final probability density of the quantum circuit's final wave function. And so instead of trying to find the entire wave function at the output of the quantum circuit, we are only interested in trying to draw samples from that wave function. And so with this in mind, right, we want to talk about whether or not existing quantum circuit simulation techniques target these properties of variational algorithms. And so let's talk about what are the existing quantum circuit simulation techniques. And here we're concentrate on two types of simulation techniques. The first style is what's called Schrodinger simulation. And in Schrodinger quantum circuit simulation, the circuit simulation is done in the form of doing matrix vector multiplications, where the vectors represent the quantum states across the qubits of the circuit. And the matrices are the unitary matrices that come from the actual operations that you're trying to do on the quantum circuit. And so to simulate the behavior of the quantum circuit, you would just multiply the unitary matrices against the state vectors. And in general, because the state vectors grow proportional to the power of the number of qubits in the quantum circuit, this style of simulation is very costly in terms of its memory footprint. And so let's compare that to the key properties of variational algorithms. We talked about how there are several key properties of variational algorithms. And then we can think about whether or not the Schrodinger style of quantum circuit simulation is able to address each of these key properties of variational algorithms. So we see, first of all, due to the memory footprint of storing really large matrices and vectors, it doesn't address the challenge of how variational algorithms may involve a lot of qubits with relatively few operations. Secondly, in this style of doing circuit simulation, each time you try to do the simulation, the computation has to start afresh. There's no way of memoizing the computational results from one simulation run into the next simulation. And so even if you're trying to simulate exactly the same circuit topology, but with only slightly different numerical parameters, you'd have to do the computation all over again. And finally, what it does excel at, what the Schrodinger style of simulation does excel at, is that you're able to use, you're able to find the full final probability amplitude wave function of the quantum circuit. And so trying to draw samples is relatively easy. Another important style of quantum circuit simulation is the Feynman style of quantum circuit simulation. In this style of simulation, the quantum circuit is phrased as a tensor network. And while we're not going to go into the details of that style of simulation, it does have different properties. So the key strengths of the Feynman style of simulation are going to be different relatively to the Schrodinger style of simulation. And for this project, what we're trying to do is try to find a circuit simulation technique that tries to address each of these properties of variational algorithms. And so finally, let's go in and talk about exactly how we use logical formulas as a way to, as a logical abstraction, as an intermediate representation that allows us to compile and reason about quantum circuits. And this is done in a style where we use a toolchain that we built that takes quantum circuits, turns them into graphical models, such as Bayesian networks. And then from those graphical models, we borrow techniques from classical inference that are specifically targeted for repeated inference and compile down the representation. And then finally, as an added benefit, we're able to try to draw samples from this compiled format. And this tool chain, each stage very nicely matches up to some of the key properties of variational algorithms. So essentially, we're borrowing this idea that using classical inference techniques, they can do things like repeated inference, repeated simulation, and also drawing samples. And that matches very nicely with the needs of doing variational quantum circuit simulation. So now let's go through these compilation stages one by one. So first of all, one insight is that we're able to use the graphical model representation, in our case, a Bayesian network, as a way to represent the quantum circuit and also the noisy, unreliable behavior of quantum circuits, all in one representation. And so here we talk about an example of a Bayesian network. This is a classic example of a Bayesian network where the Bayesian network is able to give insight on what are the truth probabilities of different events based on cause and effect dependencies, and also conditional probabilities that we know about each of these events. And our extension to this, based on various prior works that have developed this kind of formulation, is that you can use Bayesian networks. You can change the semantics of the Bayesian network so that instead of real valued probabilities, you have instead complex valued amplitudes. We can then use Bayesian networks to represent quantum circuits. And so each node of the Bayesian network would represent some qubit state in the quantum circuit. The edges between the nodes represent dependency. And then finally, within each node has attached to it a table, which is called a conditional amplitude table, which encapsulates the semantics of the qubit gates. And so in this different representation, this captures all of the ideal circuit behavior of the original quantum circuit. And also at the same time, you can encode in this format the probabilistic effects of different types of noise models. And now with this compiled representation, so this different representation, we can then move on and borrow techniques from classical inference, where we take the probabilistic graphical models and turn them into compiled representations. And this involves translations, taking the circuits and turning them into logical formulas, and turning them into different formulas that enable efficient repeated simulation. And so the key idea is that by turning the quantum circuits and turning their semantics into a logic formula, we can then make it so that this logic formula, all the variables that satisfy that logic formula represents one valid path that agrees with the semantics of quantum circuits. And in logic formulas, we know about these techniques called weighted model counting, so that once we have this formula, we can just count all the models that agree with the formula, multiply and add all the weights associated with the valid assignments, and from that get the correct semantics that allows us to simulate the output of the quantum circuits. So I just want to give a flavor of what this kind of logical formula representation would look like. So the logical formula would consist of many clauses, and each of these clauses encapsulates one piece of the semantics of the quantum circuit. And so, for example, here, these clauses denote the fact that qubit states are mutually exclusive. And then you can also, for example, use this to provide initial conditions for the quantum circuits. And in other sets and pieces of the logic formulas, you can encode other parts of the circuit semantics. So for example, here, we have other clauses that represent the semantics of a Hadamard gate, where depending on what's the inputs to the Hadamard gate and what are the outputs to the Hadamard gate, these would lead to different weights in the final model that you want to find the weighted sum of. All right. And so once you've written the formula so that you have all the semantics of each of the nodes all listed out, you can then conjoin all of the clauses together and create a giant CNF. And now with the CNF, all the logical variable assignments that agree with the CNF represents one set of qubit state assignments that agree with the semantics of the quantum circuits. And so that's the key idea and the key most important step of our transformations. In the next couple of stages, so this is a multi-stage translation, we also are able to take those formulas and further compile them down into other representations. The key idea here being that now that you have a CNF, right, we can then use techniques that researchers have developed for a long time in the area of satisfiability solvers to manipulate and compile down quantum circuits. And so there are other types of objects that you compile this down to. So one of the key final outcomes of this compilation is now we then have a arithmetic circuit. All right, so the arithmetic circuit here consists of leaf nodes that represent truth variables about the qubits and probability coin flips in the quantum circuit, and other leaves that include numerical parameters. And then between the leaves, you also have additional nodes that represent arithmetic operations. And by following the operations that the nodes tell you to do, right, you can plug into the leaf nodes truth variables about what quantum circuit outcome you want to find the amplitude of, follow the multiply and adds through the arithmetic representation, and then out from the top of this compiled representation, you will get a probability amplitude. And by working through all of the possible assignments to qubit states and random variables, you can recover the complete probability amplitude of the quantum circuit and show that you can use these techniques to do quantum circuit simulation. And as added benefit from all of this is that this type of representation is also meant to facilitate sampling outcomes from the compiled representation. And this kind of sampling is useful for simulating variational algorithms. All right, so let's quickly recap what's happened here. We've taken quantum circuits that represent variational algorithms and turn them into different representations, which we can then compile down through intermediate representations like CNFs, and finally do circuit simulation by working with these compiled representations. And this would compare to the basic way of doing circuit simulation that I outlined at the beginning, right? This is very, very distinct from the matrix vector representation, which is how we usually think about quantum circuits. Through this completely different pathway, we can still do quantum circuit simulation, and enables us to use different types of tools that we can borrow from prior research throughout computer systems. So in that chapter, I've talked about how we use logical formulas as intermediate representations for quantum circuits. And now I want to talk about how that enables us to do the task we set out to do, which is to simulate this important class of algorithms that are important in the near term called variational algorithms. And as a reminder, we talked about how variational algorithms, they have circuits that are noisy, they have relatively many qubits, but relatively few operations on each. The simulations take place many, many times, but with different parameters, but the same topology each time. And we're interested in sampling outcomes, sampling outputs from the final wave function. And through our compiled representation, it addresses each of those properties. And this leads to several interesting results. So the first interesting result is that all of this works. So we're able to use existing algorithms, ideas from classical inference. We change the semantics of the graphical models. And through that transformation, we're still able to do correct circuit simulation. So we implemented our simulator toolchain as a simulation backend to Google Circ, which is a open source quantum prototyping experimentation platform. And we're able to use our simulation toolchain to get correct simulation outputs for all of these canonical quantum algorithms, these benchmarks. And then secondarily, we use our simulation technique and we compare against both simulators based on matrix vector multiplication and also on tensor network contraction, right? So these are the Schrodinger and Feynman style simulators that I talked about earlier. And so our simulator is in the purple series here. I'm plotting the time it takes to draw samples from the quantum circuit that we're trying to simulate, plotted against the number of qubits in the quantum circuit. And this is for a benchmark that is a QAOA algorithm. As you can see, our simulation technique, once you get beyond 25 qubits, 30 qubits, our simulation performance, the time it takes for us to draw samples is favorable compared to QSIM, which is a simulator based on matrix vector multiplication. And it's also favorable compared to QTorch, which is one based on tensor network contraction. And these trends also carry over for trying to simulate noisy circuits. So this also works for quantum circuits that have some kind of noise model that models the unreliability of the operations on each qubit. All right, so I want to cap up our talk today. So in this work, the high-level key insight is we can use different abstractions to represent quantum circuits, especially noisy quantum circuits. And we can then use inference techniques that allow us to do repeated simulation these techniques that we borrowed from classical inference. And these involve really interesting transformations, such as turning a quantum circuit and turning it into a conjunctive normal form, a logical formula, and other types of data structures that allow us to do different types of queries. And this ends up being very useful for a specific and important workload, which is simulating near-term quantum algorithms that we want to study because they may be the candidates for the most useful quantum algorithms in the near term. All right. So with that, I want to wrap up our talk and thank you for taking the time to listen to this extended version of my talk. And I want to thank my collaborators, my postdoc advisor, Professor Margaret Martinosi at Princeton, and also my collaborators, Stephen Holtzen, Professor Todd Milstein, Professor Guy Vandenbroek, all at UCLA. They are the wizards of classical inference tools and languages for inference. And finally, all of this work is funded by EPIC, which is a NSF expedition in quantum computing. All right, thank you very much for taking the time to listen to this talk, and I look forward to meeting you at the panel at ASPLOS 2021. Thank you very much.